beta can change due to the following two reasons. Okay, the first reason I have already told you in the previous class, right? Changing transistor with a different beta value. Okay, so if you change a transistor with a different beta value, obviously beta value can change, and if beta changes, collector current changes, so on and so forth. Okay, now there is another phenomenon that can also change the beta value, which is the temperature. And this temperature, plays very important role in analog electronic circuits. Okay, to that matter, it impacts your solid state circuits. Okay, that's the reason, in case of electronics, okay, you normally see heat sinks, CPU fan, etc., etc. That is to keep the temperature under check. Okay, so it is observed that, okay, as temperature increases, transistor current gain beta increases. Okay, with the increment in temperature, beta increases. Okay, now for a fixed bias circuit, okay, other day you had observed that as beta starts increasing, collector current starts increasing. Okay, when collector current increases, what happens is that there is something known as collector to leakage current, okay, which is called as ICO. ICO is nothing but the leakage current. The leakage current increases. Okay, the leakage current can once again increase the temperature. Okay, so the increment in temperature can once again increase the beta value, so on and so forth. So basically what is happening, once the beta value changes in case of fixed bias circuit, the collector current increases. Increment in collector current can increase the leakage current. The leakage current in turn increases the temperature, so on and so forth. So basically what is happening is the transistor gets into a chain reaction mode. So in this chain reaction, the temperature, keeps on increasing. Okay, so due to this increment in temperature, what happens is that the transistor encounters something known as premature breakdown, and it is due to the avalanche effect. Okay, avalanche effect, and that's the reason it is also called as avalanche breakdown. Okay, so avalanche effect, right? Let's say this is a mountain. Okay, and let's say this mountain is covered with ice. Okay. Now what happens in avalanche effect is that if you roll a small snowball, okay, if you roll a small snowball from the hilltop, what happens is that as it starts coming down, it starts collecting more and more ice. Okay, so in the end, when it reaches the bottom, the mass of this snowball will be a lot bigger. Okay, this is the end mass. Okay, end mass of the snowball. So what is happening? In every roll, it is collecting the neighboring ice, and in the end, it becomes a gigantic ball, and it can, destroy the surroundings, right? Similarly, in case of transistor, what is happening is a mere rise in temperature. Eventually, what happens, what it will do is it will increase the electron and hole pair. Okay, with the increment in electron and hole pair, what happens? More current will flow. With the increment in current flow, the temperature increases. Okay, and the increased temperature can release more and more electron and hole pair. So what is happening in every cycle? These electrons and hole pairs are getting increased. Okay, so that is nothing but your avalanche effect. Okay, so avalanche effect can destroy your transistor, and which is very common in case of fixed bias circuit, provided you keep the temperature of the semiconductor device under check. All right, fine. So that's your biggest drawback of fixed bias circuit. Okay, and this is happening because your base current is independent of beta for a fixed bias circuit. And that is why the collector current changes by a large margin. Okay, so that being said, we can take up an improved version of the fixed bias circuit. Okay, so that's our second circuit for the discussion, which is called as emitter bias. You see, emitter bias is basically an improved version of the fixed bias circuit. Okay, so this is what the circuit diagram looks like. Okay, so this is your transistor. Okay, collector terminal, emitter terminal, and the base terminal. Okay, the base is connected to resistor RB. The collector is connected to resistor RC. Okay, and the common point is connected to power supply voltage VCC. Okay, in case of fixed bias circuit, the emitter was directly held at ground potential, right? But in case of emitter bias, you have a resistor connected in series with the emitter terminal. Okay, and this resistor is RE. Okay, since there is RE connected in the circuit, okay, the resulting biasing is called as emitter bias. Okay, so fine. So this is about the circuit diagram. Now let us mark different currents. Okay, so this is your collector current, okay, the base current, and this is your emitter current. All right. Between base and emitter, the terminal voltage, you can take it as VB. Okay, between base and emitter, the transistor terminal voltage is taken as VBE. Similarly, on the output side, between collector and emitter terminal, the transistor terminal voltage is taken as VCE. Okay, collector is at higher potential compared to emitter, hence upper side positive and lower side negative. Okay, so that is your emitter bias circuit. Okay, now in order to apply KVL, it makes sense to have a simplified circuit. So what we can do is we can draw the simplified circuit. Okay, you can have a simplified circuit. Fine. So next, let us draw the simplified circuit. Base, collector, emitter. Okay, you see here the base terminal is connected to RB. Okay, so let's connect it to RB. The other end of RB is connected to positive terminal of battery. So somewhere here you can connect. Okay, plus minus we will give. This we shall name it as VCC. Okay, and fine, I'll keep it here. Similarly, on the collector side, the collector terminal is connected to RC. Okay, so collector is connected to RC, and other end of RC is connected to VCC. So let's connect the other terminal to VCC. Which terminal of VCC? Positive terminal of VCC. So let's write this as VCC. Okay, fine. Then emitter is connected to RE. So let's connect the emitter terminal to resistor, and other end of resistor RE is connected to ground. Okay, is connected to ground. Okay, fine. So that's about the emitter terminal. Now, if you look at the DC source, okay, the negative terminal of DC source is connected to ground. So what you can do is you can directly bring the negative terminal of VCC to ground. Similarly, the negative terminal of VCC, let's connect it to ground on the output side as well. All right. And now let us mark the currents. Okay. IC. This is emitter current IE, base current IB. Okay, and you can also mark the terminal voltages VCE, okay, plus minus. Similarly, you can mark VBE here, okay. Lower side minus, upper side plus. Okay, fine. So this is your equivalent circuit. Okay, and write equivalent circuit. Equivalent circuit. If you compare emitter bias equivalent circuit with the fixed bias equivalent circuit, okay, the only change what you can observe is the presence of RE. That's all. Okay. Now let's see, how this RE is helping us in improving the stability of the biasing circuit. Okay. So next, what we can do is we can apply KVL. So let's apply KVL in clockwise direction for the input circuit, and in the output circuit, let me apply KVL in the anti-clockwise direction. Okay, this is how I apply KVL. Okay, next you can write analysis. Okay, so write down apply KVL to base emitter loop. Okay, as I said in the previous class, base emitter loop is nothing but your input loop. Okay, so when you apply KVL, what do you get? Minus to plus VCC, then resistance drop minus IB into RB, then terminal voltage. Okay, how are we observing the terminal voltage? Positive terminal to negative terminal, hence it is minus VBE. Okay, then you have an additional resistance drop. Okay, that is minus IE into RE is equal to 0. Okay, now this is a common emitter configuration. What is the input current in common emitter configuration? The input current in common emitter configuration is the base current, right? But if you look at your input equation, the input equation is consisting of base current as well as emitter current. I do not want emitter current to be there in this particular equation. So what I will do, I will substitute emitter current as summation of base and collector current. Okay, then I also have an expression for collector current. So that is IC is equal to beta times IB. So what I can do, in place of IC, I can substitute beta times IB. So your IE becomes IB plus IB into 1 plus beta. Or if you were to take IB common, you would get emitter current as IB into 1 plus beta. Okay, 1 plus beta. So let's say this is equation 1 and say this is equation 2. So substitute emitter current expression in equation 1. So substitute equation 2 in equation 1. So what do we get? VCC minus IBRB minus VBE minus IE. Right, what is the expression for IE? IE is IB times 1 plus beta into the leftover resistance value is equal to 0. Okay, now what you can do, you can group voltages together and currents together. Okay, so when you take out, when you bring voltage term, okay, to one side, you will get VCC minus VBE, okay, is equal to, let me bring all the resistive drops onto the right hand side. So what do I get? I get IB times, I will keep IB outside the bracket. Okay, so this is RB plus 1 plus beta times RE. Okay, close the bracket. Therefore, the base current IB is VCC minus VB, difference in potential, divided by resistance ratio, resistance value, right? So it is RB plus 1 plus beta times RE. Okay, so let's say this is your equation 3. Okay, equation 3. Okay, now I want you to observe very, very carefully over here. So equation 3 represents base current equation for an emitter bias circuit. You look at the denominator term. In the denominator term, the emitter resistance RE is getting reflected, right? Emitter resistance RE is getting reflected. Okay, and the presence is something like 1 plus beta times RE. Okay, now if I take you back to fixed bias circuit, okay, in the fixed bias circuit, okay, let me take you back to fixed bias circuit. All right, yeah, this is the equation 1. Observe, it is simply VCC minus VB divided by RP. So there is beta term missing in this particular equation, right? So no beta term is present for a fixed bias circuit. Okay, on the other hand, if you look at emitter bias circuit, there is a beta term. So what is the effect of this beta term is that if, let's say, by some reasons, let's say due to the increase in temperature, if beta rises, okay, if beta value rises, okay, if beta value rises, what happens? The entire denominator term becomes bigger, right? Because the beta is getting multiplied with RE, and the total summation, when you take, the entire denominator value starts increasing. So with the increment in beta value, what happens to base current? The base current decreases, and base current is, the collector current is directly proportional to base current, due to which the collector current will also be reducing. Okay. So collector current is given as beta times IB. Okay, that's your equation 4. So when your base current decreases, it's very sure that the collector current is going to reduce. So basically, the presence of RE gives something known as the compensation effect. So you can say that, okay, when beta increases, okay, when beta increases, denominator term of equation 3 increases, due to which base current decreases. Okay, now with the decrement in base current, the collector current decreases. Okay, when the collector current decreases, the leakage current will also reduce, and due to which the temperature gets reduced. So this is how the compensation is taking place. So the compensation has taken place due to the presence of emitter resistance. So you can say that the emitter resistor RE gives compensation effect to the circuit. Okay, thereby it increases the bias stability. Bias stability. So that's the effect. Okay, is it understood? Can you just give me a confirmation with yes or no?
Yes, sir.
Okay, fine. So that's about the base current. Okay. Next, let us apply KVL to collector emitter loop, okay, which is also nothing but the output loop. Okay, so when you apply KVL to collector emitter loop, okay, what is it? In the anti-clockwise direction, I'm going to apply. It is VCC minus ICRC minus VCE minus IER. Okay. So circuit you can observe. Okay. So it is VCC minus resistance drop minus terminal voltage minus emitter resistance drop. That is IE into RE, which is equal to 0. Now over here, okay, what you have to observe is that in the output circuit, I want collector current, right? In the output circuit, in common emitter configuration, the output current is IC, but in your equation, IC is also present as well as IE is also present. So what we can do, we know that your emitter current is approximately equals to the collector current due to the fact that base current is, very small. Base current is very small. Okay, very small in the sense when you compare the magnitude of base current with emitter and collector current, you can neglect the base current. Okay, that's because your emitter and collector current, I have told you in the introduction class that they vary in terms of millis of amperes, and IB normally vary in terms of micros of amperes. Okay, so micro is very small compared to milliamperes. Hence, you can say that IE is approximately equal to IC. Okay, due to which you can write the above equation as, okay, VCC minus IC into RC minus VCE minus, in place of IE, we can substitute IC. So IC into RE is equal to 0. Or expression for VCE can be given as VCC minus IC times sum of the resistance values. Okay, so this is your expression for transistor output voltage VCE. Okay, and let's call this equation as equation 5. Okay, so equation 3, 4, 5 talks about the expressions for IB, IC, and VCE respectively. All right, so this is how we apply KVL, and we find out the various transistor terminal voltages and currents. Okay, now let us find out, okay, few more terminal voltages. Okay, so for example, let's try to find out the expression for VB. Okay, because in numericals they'll ask you to calculate the value of VB, VC, VE, etc., etc. Okay, so first let us try to find out VB. Okay, what is VB? By definition, VB is nothing but base to ground voltage. By definition, VB is base to ground voltage. Okay, let us mark the base to ground voltage in our circuit diagram. So base to ground voltage, as in this voltage, this is VB. Okay, this is base terminal and this is your ground terminal. Okay, this is positive and this is negative. So base to ground voltage is equal to what? Base to ground is equal to base to emitter plus emitter to ground. Okay, so base to ground voltage can be written as base to emitter plus emitter to ground. Okay. Emitter to ground. Okay, pictorially something like this I can show you. Okay. Let me go for an exploded view to add better clarity. So this is your ground terminal and this is your emitter terminal. Okay, so what we are interested in finding out this voltage. Okay, base to ground voltage. So base to ground voltage is nothing but base to emitter voltage plus emitter to ground. This is what I was talking about. Okay, so this is RE and this is IE. Now it is clear, right? So VB is equal to VBE plus VE. Okay. Similarly, VE, straightforwardly you can write on. VE is nothing but emitter to ground voltage. Emitter to ground voltage. Okay. So what is VE? Emitter to ground voltage. Between emitter and ground, what do you have? You have a resistor RE through which current IE flows. Hence, the voltage drop is IE into RE. IE into RE. All right. Done. And finally, we have VC. VC is defined as collector to ground voltage. Okay, collector to ground voltage. So collector to ground voltage, what you can do is you can measure it from the collector terminal, okay, till the ground terminal. Okay, so this is your collector terminal. Okay, so between collector and emitter terminal, you have VCE, and between emitter and ground terminal, you have VE. Okay, so voltage measured across collector terminal and the ground terminal. Okay, between collector and ground, what do you have? You have two voltages, collector to emitter plus emitter to ground. So on that note, you can write VC is equal to VC plus VE or VC plus IE into RE. Okay. Is it understood? Any doubts? Can you quickly confirm?
It's clear, sir.
Clear. Okay, fine. If that is understood, we can take up the load line analysis. Load line analysis. Okay. So for load line analysis, okay, you know that load line analysis is constructed on transistor output characteristics. Okay, so we need to look at the transistor output equation, which is equation 5. Okay, so let me rewrite the equation. So VC, the transistor output equation, VC is equal to VCC minus IC times RC plus RE. Okay, so this is your X variable and this is your Y variable. So we'll put one variable as 0, okay, while finding out the intercept value of the other. Okay, so put X, not X, put, let's say, VC is equal to 0. Okay, so when we put VC is equal to 0, we get VCC is equal to IC into RC plus RE, or IC is equal to VCC divided by RC plus RE, which is the maximum value of collector current. Hence, we can rename it as IC saturation. Okay, so this IC saturation serves as your Y-intercept. Okay. On the other hand, when you put the Y variable as 0, that is IC as 0, you get VCC is equal to VCE, and this VCE represents the maximum VCE value. Hence, you can write VCE saturation. Okay, so this VCE saturation basically represents the x-intercept. X-intercept. Okay, so having known the x and y intercepts, you can draw the load line graph. Okay, all right. So let's quickly construct the load line graph. Okay. Y-axis, then your x-axis. Okay. Name the axis. This is your current axis. This is your voltage axis, expressed in volts, and this is normally expressed in millis of amperes. Okay, once that is done, you can mark your respective y and x intercepts. So this is your y intercept and this is your x intercept. Okay, so y intercept value is IC saturation and x intercept value is VCE saturation. Okay, once these two have been placed in the load line diagram, what you can do is you can join the 2 points with a straight line. Okay, all right, so that gives basically the load line. Okay. This is your load line. Load line. Now, one quick question. Tell me the slope of this load line. What is this slope? Quickly. Who can tell me the slope of this load line? You don't have to solve. By inspection method, you can say. The slope is always the reciprocal of the output resistance. If you look at the output equation, what do you get the output resistance as? You get the output resistance as RC plus RE. If your output resistance is RC plus RE, then your slope going to be minus 1 by RC plus RE. Okay, so slope is always negative. I've told you, right, in the previous class, because it is kind of downgoing ramp. That's the reason. Okay, this is your upgoing ramp. Okay, and this is your downgoing ramp. Upgoing ramp will have positive slope and downgoing ramp will have a negative slope. Is it clear?
Yes, sir.
Okay, fine. So that's your load line. Okay, fine. So this is about your emitter bias circuit. Okay, so what I will do, I will do the problems in the next class. Okay, so as of now, what I will do, I will consider the third biasing network. Okay, the third biasing network is collector to base bias. Okay, the third biasing network is collector to base bias. Okay, so collector to base bias. Okay, it is something like an improved version of emitter bias circuit. Okay, improved version of emitter bias circuit. Okay. Fine. So the circuit looks like this. The circuit diagram. The transistor. So this is your collector resistor. Okay. Now you have to be little careful over here. In case of collector to base bias, okay, this is your collector terminal and this is your base terminal. What you have to understand is that between collector and base, there is a connection. That's the reason the name is given as collector to base bias. Okay, so between collector and base, the connection is established by placing a resistor in between. So this is your resistor RB. Okay, so this is the connection diagram. And at the emitter side, you have to just follow the emitter bias notation. That is, place a resistor between emitter and ground. So this is your RE. So this is your collector to base bias. Okay. Now, this is plus VCC. Okay. In case of fixed bias as well as emitter bias, okay, the other end of RB was directly connected to VCC, right? Over here, the other end of RB is connected to, collector terminal directly. Okay. By doing that, what you can do is you can slightly alter the current flow. Okay. In the sense, okay, see, through RB, base current flows, and into the collector terminal, which current flows? The collector current IC flows. Okay. So what is the current that flows through RC? Can anyone tell me? Into the base terminal, base current flows. Into the collector terminal, collector current flows. So what is the current that flows through RC?
IB plus IC.
Exactly. IB plus IC, which is nothing but actually IE, the emitter current. Okay. So this is the exception. Okay. This is your IE. Okay. And this is your VB plus and minus. Okay. And across emitter and ground, okay, you have VE, which is again upper side positive, lower side negative. Okay. Now, can anyone tell me what is the, okay, what I will do, just to add clarity, I will write this RB inside. Okay, the base resistor, let me write it inside. Okay, so across resistor RB, what is the voltage drop? IB into RB. Okay, this is plus, this is minus. Okay, and across RC, okay, that is this terminal. That is from power supply terminal till here. Till here. What is the potential? It is RC into IC plus IB. Okay, IC plus IB. All right. So on the output side also, let us mark the terminal voltages. This is your VCE plus and minus. Okay. Till here, let me draw. Okay, and this is your VE. Okay, which is true for the input circuit as well, right? On the input circuit also, I have marked VE. That's okay, right? And again, this potential, that is potential across resistor RC, can be given as RC into IC plus IB. Once again, you can write the potential across RC as RC into IC plus IB. Okay. Now, in collector base bias, what I will do is I will not construct the equivalent circuit. Okay. That's because if I construct an equivalent circuit, basically, instead of getting the easy KVL equations, we will end up in getting complicated KVL equations. So that's the reason, as it is stated, I am trying to apply KVL. All right. So what I will do, I will first mark the input loop as well as the output loop. Okay, you know that input loop is base emitter loop. Okay, so anything that lies, okay, on the left hand side is your input loop, and anything that lies on the right hand side is your output loop. So what I will do for the input loop, I will just mark the region. Okay. Okay, so this region, okay, okay, the left hand side region is my input loop, and from this imaginary axis, okay, anything that falls on the right hand side, for us it is going to be the output loop. Fine, clear? Okay, now you apply KVL for the input side as well as output side, okay, using you know, a very interesting technique. Now, can anyone tell me what is the potential measured from, okay, this node to this node? Who can tell me what is the potential measured from this node to this node? What is the potential from this node to this node? Can you type your answers? I'll give you, say, 2 minutes of time to observe. I have marked the nodes, okay, and the nodes are present at the extreme top and at the extreme bottom. And what is the voltage you will get between those two nodes? Type your answers. See, without your support, my efforts will fail. Right or wrong, that is secondary. What voltage you get between this node and this node? Can anyone tell me? Okay, IERC plus IBRB plus VE. Correct. That is equal to what, Rakesh? Because when you write KVL, LHS is equal to some RHS you will write, no? So what is your RHS term, say for example?
0.
Absolutely, that's what I wanted. That is VCC. Okay, so this is how we apply KVL in this particular case. Fine, good, Aniket and Rakesh. Okay, so this let us mark it as VCC. So I can mark VCC on the input side as well as I can mark VCC on the output side. So this is also VCC. Okay, minus, plus, minus, plus. Okay, so now let me write, apply KVL in the base emitter loop. Okay, so when you apply KVL in the base emitter loop, okay, you will get summation of potential. Okay, summation of potential difference or drop across RC, drop across RB, drop across RE, as well as terminal voltage VB. Okay, so you have first drop here, second drop here, okay, and the potential, terminal potential between B and E over here, and finally you have your emitter to ground potential. So it is IBRB, sorry, yeah, IBRB, okay, I should have started from here, IC plus IB, right? IC plus IB into RC into RC plus the second potential drop, which is IBRB, plus the third potential, which is VBE, plus the fourth potential, which is IE into RE, okay, which is equal to the power supply voltage VCC. So that's my KVL equation. I will, don't worry, I will just bifurcate the terms. So this is your term 1, term 2, term 3, term 4. So summation of, all the EMFs and the potential drops is equal to the battery potential, which is VCC. Okay, or we know that IC plus IB. Okay, we know that IC plus IB is IE, and IE can also be written as 1 plus beta times IB. Okay, so we can apply, this particular equation in the first equation. Okay, so substitute equation 2 in equation 1. Okay, I'll write VCC on the left hand side. Okay, that's the usual way, right? So doesn't matter even if you keep it on the right. Okay, don't break your head. So IC plus IB is IE, and IE can be written as 1 plus beta times IB. So what I will do, I'll write this as 1 plus beta times IB into resistance RC plus IB into RB plus VBE plus IE into RE. So IE can be written as 1 plus beta into IB into RE. Okay, or we can write IB as difference in potential, that is VCC minus VBE divided by the resistance values, right? So we have taken IB common, right? When you take IB common, what are you left with? You will left with RB. So let me write RB here, plus, and when you take out IB common from the first term, okay, you are left with 1 plus beta into RC. Similarly, from the last term, when you take out IB as the common factor, you will be left with 1 plus beta into RE. Okay, this is RE. Okay, fine. So you know that in the first term and in the last term, 1 plus beta is common. So probably you can keep 1 plus beta outside the bracket. Okay, so you will get a much simplified version. So it is RB plus 1 plus beta times RC plus RE. RC plus RE. Okay, so this is your base current expression. Base current expression. Let's call this equation as equation 3. Okay. Any questions? Any questions till now? Did you understand?
Yes, sir.
Any doubts? No? Okay, fine. So that's your IB. So having known IB will enable you to find out IC. So IC is beta times IB. Okay. So let's take this expression as 4. Okay. Once again, you can draw a quick note, okay, from equation 3 that when let's say beta gets changed due to temperature or due to the incorrect transistor replacement, okay, when beta changes, okay, what happens? Collector current increases. When beta increases, collector current increases. Okay, but in the meantime, what will happen with the increment in beta value? Okay, with the increment in beta value, the denominator term increases. Okay, denominator term increases. So your base current decreases. So even in case of collector to base bias, okay, so when beta increases, okay, so this I will just strike out because I want to state an improved statement. So when beta increases, as per equation 3, IB decreases, right? With the decrement in IB, the collector current increases, and therefore Q point is kept stable. Okay, kept stable. So you can say that even a collector to base bias circuit provides compensation through emitter resistor RE. Okay, so your emitter bias and collector to base bias, okay, gives something known as negative feedback effect. Okay, something known as negative feedback effect. Now, what is this negative feedback? Negative feedback is something like, it's a feedback that tends to reduce the error. So here the error is the changes in the collector current. Okay, so it tries to bring back the collector current to its original value. So in that sense, you can call it as a negative feedback effect. Okay, so this is very important. For Viva as well as for short modes. Okay, all right. So finally, okay, I have 4 minutes, right? Okay, no issues. Output circuit. Apply KVL. Okay, so apply KVL in the output circuit. What do you get? VCC minus IC plus IB into RC minus VCE minus IE into RE is equal to 0. So IC plus IB can be taken as IE. Okay, now in the output loop, we can take IE approximately equals to IC. Hence, you can rewrite the above equation as VCC minus IC times RC minus VCE minus IC times RE is equal to 0, or you can write VCE is equal to VCC minus IC into RC plus RE. Okay, so this is your output equation number 5. Okay, so if you observe equation number 5, it is pretty clear that this equation is similar to emitter bias equation, and therefore you should get a similar load line graph. Okay, because output equation is same. If output equation is same, then quite obvious that the load line will also be the same. Okay, so quickly let me construct the load line. This is IC in milliamperes, VCE in milliamperes. So when you put IC is equal to 0, okay, you get VCE is equal to VCE saturation is equal to VCC. And on the other hand, when you put VCE is equal to 0, you will get IC is equal to IC saturation is equal to VCC divided by RC plus RE. Okay, this is your x-intercept and this is your y-intercept. Okay, in short, let me call it as point. Okay, so this is your y-intercept and this is your x-intercept. IC saturation and VCE saturation. Join the two lines that will give you the load line. Okay, once again, the slope of the load line is minus 1 by RC plus RB. Okay, so that concludes today's session.